Good afternoon to everyone. On behalf of KSR College of Arts and Science for Women, I welcome you all to the final day of our faculty development program of Science and Technology Development Academic Growth. We are honored to have with us today Dr. Rajesh Pandian, Department of Microbiology, Bharatidasan University, Trichy. Over the past days, we have explored topics such as development of nonlinear optical material for practical device application, atomic scale hybrid nanostructure, differential calculus and matrix theory in science and engineering and technology, science and technology development in research, synthesis of small heterocyclic compounds, science and technology development in energy, environment, and healthcare application, which have greatly enriched our understanding. Today, to begin today's proceedings, let's invite Mrs. S. Mohanapriya, Assistant Professor, Department of Mathematics, to deliver the welcome address.
Good afternoon, everyone. Good afternoon to everyone. It's my honor and privilege to welcome you all to this faculty development program on Science and Technology Development Academic Group. On behalf of KSR College of Arts and Science for Women, Tiruchendur, I extend a warm welcome to all dignitaries, resource person, and faculty members who have joined us for this faculty development program. With the blessing of our beloved founder, late line Dr. K.S. Rangasamy, MJF, a warm welcome to our chairman, Mr. R. Srinivasan, in absentia. I would like to welcome our young, energetic Vice Chairman, Mr. Sachin Srinivasan, in absentia. A cordial and heartfelt welcome to our Principal, Dr. M. Karthikeyan, KSR College of Arts and Science for Women, Tiruchendur, who has been the backbone of this event in absentia. We are deeply honored to have with us today's chief guest, Dr. Rajesh Pandian, Department of Microbiology, Bharatidasan University, Tiruchirappalli. Their achievement and dedication to the work serve as an inspiration to us. It's my glad to welcome you all the participant for the seventh day faculty development program. Once again, I welcome you all. Thank you.
Next, I summon Mrs. E. Mainavati, Assistant Professor, Department of Mathematics, to deliver the address of our today's chief guest, Dr. Rajesh Pandian.
Good afternoon, everyone. It gives me great pleasure to introduce the chief guest, Dr. Rajesh Pandian, who has accepted our invitation to join us seventh day faculty development program on science and technology development academic growth. Dr. Rajesh Pandian has received his doctoral degree from Department of Microbiology, Bharatidasan University, Tiruchirappalli, as well as he has served as the assistant professor in Department of Biochemistry, KSR College of Arts and Science, Namakkal. He has received National Postdoctoral Fellowship at Department of Parasitic Technology, Anna University, Tiruchirappalli. He has received a postdoctoral research associate in Department of Civil Engineering, University, Republic of South Korea. He has teaching experience in the Department of Biochemistry, Karpagam Academic of Higher Education, Coimbatore. He has 17 years of research experience and published 60 research and review articles and 5 book chapters and 5 special editions and participated in more than 80 national and international conferences, seminars, symposium, workshops, webinars, and faculty development program. He has organized seminars and workshops by his lead. He was invited as a resource person from many reputed organizations. He has received national and international funds for the research. He has guided M.Sc PhD students in his research career. He has many awards and honors in many editorial academic professions and also having membership in many professional bodies. He has experience in the tissue engineering by using various biological materials like Bombix mori, Gallus domestics, also who is working in the field of environment microbiology, particularly wastewater treatment, COVID waste management, and dye degradation with materials chemistry and nanotechnology by using various transition metals and metal oxides. As well as he is experienced in various research for the pharmaceutical pharmacological approaches. He is experienced in pharmaceutical preparation, nano emulsion, and their analytical evaluation. I would like to express my gratitude to all of you for being here. Your presence is greatly appreciated, and we are honored to have you join us in this faculty development program. Welcome you, sir.
Thank you, ma'am. Thank you for the warm welcome and nice introduction about me. And this is a great day to share you all my research experience in the foreign country, South Korea. So we are working in the nanoparticles and nanostructures. This is the entire concept of we are going to discuss today about the materials, how it is useful to the environment and society. So whatever the thesis and dissertation we are having here, we are simply stopping and dropping at the point while we are going to the societal needs. So at the time, we have to carry on the research to the society users. So that is our ultimate aim of current research. So shall we go to the presentation? Are you able to hear?
Yes, sir.
Yeah, thank you. Are you able to visit my page? What I share?
Yes, sir. Yes, sir.
Yeah, okay, thank you. So ultimately, we are entire society needs that the particular purified water. So always in metropolitan city contaminated with the industrial effluent. So that is the ultimate aim of our present study to eliminate the toxic materials in the wastewater and how we are controlled the pollutions or pollutants to the river, lakes, pond, puddles. So likewise. So our aim of the study, non-toxic SGO. So we know very well about the catalyst. Catalyst cannot be or should not be disturb the water system or any material, but it has to forward the reaction from the wastewater to normal water or purified water or any material to purified material. So our particular aim is to focus on the wastewater treatment. So sulfonated, non-toxic sulfonated graphene oxide, sulfonated carbon nanotubes, and sulfonated titanium oxide. Nanomaterials doped, that is the doping, it's stuffed, and the ultrafiltration membranes for the application in wastewater treatment. Sorry, that is stuck. Yeah. So the present study abstract that explains that the application of nanocomposite materials in membrane bioreactors. So always our water treatment plant, they are constituted with the membrane bioreactors that is known as abbreviated as MBRs. MBRs is cute, attractive because of their great potential to enhance the filtration performance and anti-fouling of bacterial population. While you are keeping a mug or any vessels inside the water flowing area, so you can feel that mug or any vessels, a slight appearance of fouling bacterial population inside the vessel or mug. So wherever it may be a restroom or it may be a sink of our kitchen. At that time, you can find some fouling. So that is called for bacterial population. So we have to eliminate. If in cold time, we know very well about we have to heat the water and we are consuming that heat water. So at the time, we are eliminating the bacterial population and we are obstructing the growth of such bacterial population. So that is known as anti-fouling. So on the other hand, the inherent antibacterial activity of nanoparticles is a significant obstacle which can adversely affect bacterial growth and the microbial community in MPRs. In this study, modified polyvinylidene fluoride, that is known as PVDF, and polyether sulfone ultrafiltration membranes, we are prepared here for the sulfonated graphene oxide and carbon nanotubes. And with the help of titanium oxide, this is the transition method. It can be emitted, the H nu is equal to delta. You know very well the photon energy converted into heat energy. That heat energy can eliminate the bacterial population and toxic materials which is present in the wastewater. Then it is converted into purified water. So the antibacterial effect of nanoparticles and the non-toxic properties of nanocomposite materials and membranes were examined using three different gram-negative bacterial populations, which is isolated from Daegu region of South Korea, where I was stayed there past 4 years back. So that is Escherichia coli, Pantoagglomerates, and Pseudomonas graminis. The results showed that the PVDF SGO, that is sulfonated graphene oxide, sulfonated carbon nanotubes, and P polyethylene sulfur, sulfonated titanium oxide. These are the three materials we have taken for the evaluation of such material to be used for the wastewater treatment. Approximately 50% of the antibacterial activity was observed in the disk diffusion and viability test under transmission electron microscopical analysis. On the other hand, the ultrafiltration membrane showed significantly high non-toxic properties, uh, greater than 95% significance, that is P less than 0.001, indicating that they are focused to bacterial growth. This paper reports that the PVDF SGO, PVDF SENT, and PES titanium oxide nanocomposite membranes are more sustainable than the PVDF membrane and are promising materials for MBR because they are non-harmful to antibacterial activity. Over the past decade, bioenvironmental technologies utilizing various nanomaterials, that is the past year, decade, I told that 1960s, 1960s, they were started about that the purification of wastewater to the MBR system and converted from the wastewater to RO water, that is reverse osmosis water. That performance for sustainable water industry and non-absorbance bioelectrocatalysts and nanocomposite membranes. In membrane bioreactor technology, nanocomposite membrane has a great potential to improve the filtration performance and anti-fouling. However, antibacterial activity of nanocomposites is significant and disadvantage also can be impacted to bacterial growth and microbial community in the MBR, microbial uh, membrane bioreactors. In general, antibacterial activity in an important characteristics to kill microorganisms microbial growth. So while we are consuming the water, it should not be have the toxic substances as well as the bacterial population or any contamination. Various antimicrobial nanomaterials have been developed to control microbial induced diseases and bacterial growth. This is the methodology we have followed. Wastewater collection from the different Daegu region of South Korea, isolation of bacterial species, identification of the bacterial species, preparation of nanoparticles, antibacterial properties, and preparation of ultrafiltration membranes, non-toxic properties of ultrafiltration membranes, and publication. Overall research, how the anti-fouling membrane is prepared and how it is used for the antibacterial property and eliminating the toxic substances present in the wastewater. So this is the entire study that shows that the membrane bioreactor that is constituted with the ultrafiltration membrane that is known as UV membrane that is also constituted about that the nanoparticles, how it is eliminating the toxic substances and how it is converted into reverse osmosis water that is known as RO water. So this is the entire setup. The picture represents that the how the feed tank is feeded with the wastewater and how the module is eliminating the bacterial population and toxic substances that is known as permeate tank, and how much quantity of bacterial culture was found in that wastewater nature. Come to our research, graphene oxide and its sulfonated graphene oxide, a nano preparation of for non-toxic ultrafiltration membranes. This is the some images of scanning electron microscopy of the graphene oxide. This is known as graphene oxide sheet. It looks like a paper. So it cannot be able to see in naked eye. Naked eye, we cannot be see, which will be look like powder. But if you go through the scanning electron microscopy, you can find that the sheets of graphene oxide. So this is known as graphene oxide. This is sulfonated graphene oxide. So sulfonation will be placed here, treated with the sulfuric acid, H2SO4. So how it is applicable to the wastewater? So we are prepared the nano synthesis of graphene oxide and sulfonated graphene oxide. That graphene oxide treated with the three type of bacteria that is known as E. coli, Panthoagglomerans, and Pseudomonas graminis. These are the virulent bacterial population found in the Daegu region of South Korea. So how it is eliminated? In 250 minutes, the graphene oxide and sulfonated graphene oxide eliminating the bacterial population. So through this graphical representation, we can found that the nanoparticles are more significant for the eliminating the bacterial population present in the wastewater and converted into normal water, that is RO water. So this is the representation of figure representation like that cell viability. How much viable means the cell can grow. So how we are obstructing their growth, or abruptly cleave the cell wall and treated with the nanoparticles, how it is converted into RO water. So first of all, we have isolated the E. coli and treated with the nanoparticles, graphene oxide in the dosage of 250 microgram per ml and sulfonated graphene oxide 250 microgram per ml. In subsequently, Pseudomonas agglomerans and Pseudomonas graminis, Panthoagglomerans and Pseudomonas graminis. So these three bacteria are eliminating the bacterial population in the uh, colony forming units called 10 to the power of 6 CFU per ml. Okay, and we are clearly observing that the bacterial population present here, the E. coli. So this is cell wall is not cleaved or damaged. So clear cut of the external cell wall, and this is Panthoagglomerans and Pseudomonas graminis. So while with the GO and the SGO, you can see the cell wall abruption and it is cleaved. Entire cytoplasm is cleaved and outer. The same images of the PVDF GO and the PVDF SGO membranes, that is polyvinylidene fluoride and graphene oxide and sulfonated graphene oxide. This is the uh, ultrafiltration membrane. So you can see here the pore sizes which can penetrate the water and eliminating the dust material and toxic material or bacterial population in the pores, and we can collect the purified water through this pores, look like a filtration paper. So likewise, sulfonated graphene oxide. So this is the cell viability after treatment with the membrane bioreactor ultrafiltration membrane. E. coli is slightly reduced. The population is reduced through the observation of the graphical representation. E. coli, Pantoagglomerans, and Pseudomonas gramineus. So this is the entire study defined that the cell viability of non-toxic PVDF membrane, which cannot be toxic to the water, but it is toxic to the toxic materials. So, and also bacterial population. It is reducing the bacterial population and toxic materials. So then we are moving to the carbon nanotubes, and it's sulfonated carbon nanotubes, a preparation for non-toxic ultrafiltration membrane. So this is entirely defining and clear-cut evidence of the nano-synthesized carbon nanotubes. This is the sulfonated carbon nanotubes. So sulfonation will be go through the tube. So entire carbon nanotube in slightly you can observe the buds are found in the tubes. That is sulfonation. This is also same explanation or explanation and definition what we have observed in the sulfonated graphene oxide. So carbon nanotube treated with the E. coli, agglomerants, and gramineous. So sulfonated carbon nanotubes also treated with the bacterial population, and it is reducing at the minutes of 250. Okay, and zone of inhibition found that the reduced colonizing in the wastewater treatment. The same concept here, cell viability test toxic to the bacterial population, E. coli, agglomerants, gramineous. So how it is reduced. So we are getting the clear-cut evidence of that significant reducing bacterial population in the wastewater, and we are receiving the RO water, reverse osmotic water. Bacterial cell viability, toxic uh, CNT and SCNT, that is sulfonated carbon nanotubes. Here also we are evidencing that the some images of bacterial cell wall, entire wall collapsed through the treatment of carbon nanotube, 2 micrometer observation, and sulfonated carbon nanotube at the 2 micrometer observation. The cell wall is ruptured, and the entire system of the bacterial cell wall is collapsed. Here we can observe that the carbon nanotube are surrounded. How to eliminating the bacteria? How to eliminate the bacteria? So here the sulfonated carbon nanotubes also observed that how the carbon nanotube is eliminating the bacterial population from the wastewater to converting as the RO water. This is the FESEM scanning electron microscopy images of PVDF CNT and PVDF SCNT UF membranes. So here we can find that the pore sizes. So how we are filtering the bacterial population. Here the transverse section of the membrane, ultrafiltration membrane. So how accommodating that the pores are having the carbon nanotubes and sulfonated nanocarbon tubes. So CNT and SCNT. So these pores are receiving the bacterial population which is present in the wastewater and eliminating the bacterial population and toxic materials which is present in the wastewater and converting the wastewater to purified water at the rate of 80 percentage. Here the same concept here we are treating with the carbon nanotube and sulfonated carbon nanotube, E. coli, agglomerants, and Pseudomonas gramineus. How it is eliminating the three types of bacterial population which is present in the wastewater. Again, the PVDF carbon nanotubes and PVDF sulfonated carbon nanotubes. This is the ultrafiltration membrane, how it is eliminating the bacterial population in the present in the Petri plate, how the bacterial population is reduced through the incorporated carbon nanotubes in the PVDF, that is known as polyvinyl fluoride. So next we are moving to the third concept of third material, titanium oxide. Titanium oxide. Wait for a while. Sorry. Sorry for the interruption. Okay, thank you. Titanium oxide and its sulfonated titanium oxide, this is the transition metal while we are approaching with the uh, UV light, ultraviolet light, or normal visible light. This is a normal visible light providing some photons to the titanium oxide. It is expressing their photon energy to the heat energy. So it is converted photon and photon energy absorbed from the light source, that is that may be sunlight, that may be UV light, that may be laboratory UV light, or else visible light. So that light sources will be absorbed through the titanium oxide, and then it is converting into heat energy. That heat energy killing the bacterial population which is present in the wastewater and converted into RO water. So this is the titanium oxide structure through the scanning electron microscopy. Uh, this is sulfonated, look like a small spherical and ovalate in structures in some of differentiation between the ovalate and spherical. So this is the disk diffusion method, toxic titanium oxide and sulfonated titanium oxide. Same methodology we have followed for the disk diffusion method, E. coli for the three bacterial population agglomerants and gramineans. So the cell viability test for the toxic titanium oxide for the three bacteria, which is followed for the previous studies. Look like the previous study. Bacterial cell viability test while treating with the titanium oxide. Here we can see the evidence of such titanium oxide particles surrounded the bacterial population and a single bacteria, and it's rupturing the cell wall and entirely cleave and decaying the nativity of their growth, and it will be eliminated from the wastewater to the purified water. This is the ultrafiltration membrane structure. The pore size is observed through the SEM images, scanning electron microscopy. This is the bacterial cell viability test, non-toxic PES titanium oxide ultrafiltration membrane, how it is eliminating the bacterial population. You can observe um, observed that the eliminating of bacterial population of three types of bacteria, which is isolated from the Daegu region of South Korea. The bacterial cell viability of non-toxic PES membranes, which look like a white in color, because titanium oxide in white color. So that membranes are kept in the petri plate, and how it is eliminating the bacterial population. About the three bacterial population, coli, agglomerants, and gramineans. So this is the entire graphical representation of the how we are converting the material to the societal use, and how it is used in the our RO system in our entire metropolitan cities are using the RO system, not to the corporation water, because of bacterial population is high in the river water. Such a way we are creating that the nanoparticles, which is treated with the ultraviolet membrane and uses for the RO system, reverse osmosis. RO water அப்படின்னு நம்ம சொல்லிக்குவோம்ல. ஸோ அந்த RO வாட்டர்ல இந்த நானோ பார்ட்டிகல்ஸை சிந்தசஸ் பண்ணி இன்கார்பரேட் பண்ணும்போது how it is eliminating the bacterial population, and we are going for the further purified water. We are receiving the purified water from the RO system. So at the conclusion of that, the materials we have prepared, the fabricated prepared materials was observed how the nanoparticles were synthesized. Sorry for the interruption. The prepared nanoparticles are how it is useful to the bacterial elimination and ultrafiltration incorporation and the UF membrane preparation, that is ultrafiltration membrane preparation, and how it is used to eliminating the bacterial population present in the wastewater, and how we are converting the wastewater to RO water. So the modified membranes were non-toxic to 3 different bacterial species were observed from the Degradation of South Korea, and 90% of the population was still alive. And while treating with the ultrafiltration membrane, entire population is reduced, and therefore these membranes could be um, quite useful in wastewater treatment plant, that is known as WWTPS, to control the bacterial population without disrupting the microbial function of the MBR system. So these are publication. We are having the ecotoxicology and environmental safety impact of salmon. This is the first authorship was made through this entire study. It was studied in laboratory of South Korea. Sivashankaran Ayuru and colleague of Yang Hu An. This is the next journal of photochemistry and photobiology, biology, 6 impact factor. Rajesh and myself and one more colleague, Shanmuga Magalingam, and my one more colleague, Yang Hu An. This is the third impact factor journal, Chemical Engineering Research and Design, and 3 authors. We have published 3 publications regarding to this paper and research. This is my professor who is encouraged for the work, and this is my entire team worked for the ultrafiltration membrane. We have published enough 200 papers in our laboratory. And thank you, Onudal, for your all presence and make me for your keen interest with my topic, research topic, which was done in South Korea for the past 4 years back. So thank you, one and all, and thank you the management of KSR College of Arts and Science for Women, and principal of KSR W, Dr. Karthikeyan sir. He is my close friend. At the time I was stayed there in KSR CAS. So I would like to thank our organizer for the invitation to share my research findings. So entire team and the participants of this FDP program. So thank you one and all for your patience. Thank you and all. The session is open for discussion. If you have any queries and clarification, you can raise your question.
The floor is now open for question. Please feel free to share your ideas and thoughts. Thank you. Participants can feel free to share your thoughts or ideas or any queries. You can ask now.
So good afternoon, sir.
Yes, ma'am, you can proceed.
Good afternoon.
Sir, actually, I'm from chemistry department, sir. So my research work is on coordination compound preparation, sir. So
Okay.
for that, what kind of biological studies we can proceed, sir?
Coordination chemistry you can use for the dye degradation. So if you go for biological things, which will be very difficult to handle.
Okay, sir.
While even though I am a chemist in my bachelor's, so I was used that the particular coordinate compounds for the dye degradation, because dye is also having a wide range of phenanthrene rings.
Okay.
Even though azo dyes are having a wide range of phenanthrene ring and benzene rings. So we cannot
Okay.
be able to degrade the dye from the wastewater. So at the time we can focus on that dye degradation. So if you go for the bacterial population, that is very difficult to handle,
Okay, sir.
because bacterial population easily uptake the coordinate chemicals,
Okay. Okay.
coordination chemicals. Yeah, sure.
Thank you, sir.
Thank you.
Any other queries, questions? Participants can feel free to share your thoughts. Any other questions? Questionary session it is. I request to all the participants to turn on your camera for a while to take photo. Thank you. I summon Ms. D. Bhuvaneshwari, Assistant Professor, Department of Mathematics, to present the vote of thanks.
Gratitude unlocks the fullness of life. It turns what we have into in a fun way. It's my privilege and honor to extend a vote of thanks on this memorable occasion. First and foremost, I would like to express my heartfelt gratitude to our special guest, respected Dr. Rajesh Pandian sir. We are deeply grateful for the insightful presentation on bimetallic nanoparticles for antimicrobial activity and dye degradation application. Your expertise and guidance have been highly enlightening, and we are appreciate the time and the effort you look to share your knowledge with us. A special thanks to our principal, vice principal, and the directors of the academy in absence here. And I would like to thank HODs and faculty members for this grateful session. I would also like to extend my thanks to our organizing committee who have worked to make a session a grand success. Thank you, participants, for your cooperation on today's session. Thank you all.
Thank you, madam.
Thank you, ma'am.
Thank you, ma'am.
Shall we go back?
Yes, sir. You can wind up, sir.
Thank you. Thank you all.
Thank you, sir. Thank you, sir.